I'm not sure I can.
I'm recording now. I'm recording now. Okay, so hello everybody to this virtual EPR meeting. So you should have now gotten a notification that we're recording. So if you don't want to be on it, well, just don't say anything basically. So you're not on the video. So just some organizational things. So at the end we will have a discussion, and you can kind of digitally raise your hand in Zoom. So you go in the participants panel, depending on your client, you should be able to raise your hand. Yeah, because I don't always see you if you're waving in your video or in the chat. Then if you want to keep up to date to see the program, you can go to the IES webpage under online activities. So that's the International EPR Society, which help us with the organization of these meetings. And then also, if you would like to give a presentation, or if you know somebody or some of your PhD students you think it's should give one, feel free to tell us. So the email address is also on the webpage, or you can contact me directly. So today we have Mathur Srivastava from Cornell University. He has an undergrad and master's degree in electrical and computer engineering. Then he did his PhD under Jack Fried at Cornell University. And recently he started his faculty position at Cornell as an assistant research professor. And there he's establishing his signal science lab, so his research group. And today he's going to talk about whether the wavelet denoising is the snake oil or not. I'm going to stop share and then you can take over, Mathur.
Thanks, Nino. First of all, happy Friday. And I welcome all the friends coming from Europe waiting for what you call this night to over and start your party, whatever that is. And as well as people from California who are basically joining up, getting up early in the morning and having their coffee. Today, I want to talk about wavelet denoising and how it can help us help us basically in ESR spectroscopy to study some of the structural biology problems that we are not able to do until now. So let's look at the state of the art technology currently, where EPR is currently. So we have these modern spectrometers where we can study, we have CWESR, pulse dipolar spectroscopy, 2D ESR, where you can study both dynamics and structure for a wide range of conditions. And then we have these biological systems that are basically ready to be studied and needed to be explored. And then we have this site-directed spin labeling, which allows us to study these biological systems with these modern ESR spectrometers. So we have developed over the past few decades a lot of these technologies which we can help solve a lot of intelligent questions. And in terms of capability, collectively, if you see, we can measure distances, study distances ranging from 0.1 nanometer to 10 nanometer. We can go as low as some micromolar concentrations and certainly above. And we can study things in cryo-EM and room temperature. And in particular, we can study dynamics from nanosecond to microsecond scales at a nanosecond snapshots. So we are doing pretty well. But what is that which has left us basically stop us from addressing some of the challenging questions? It is always insufficient signal strength. So we have all this modern technology, which has so much capability, but we still have insufficient signal strength, as many of you may have encountered. So what do we do? There's ESR technology, which is the queen. Say, I rule the world. But there's another thing. I'm the husband and I'm the data processing. I can help you. She said, I don't need your help. I am the crown. I have everything. But to have kids, you need a husband. So how can data processing help us to overcome this insufficient signal strength? And how can we use this technology to overcome this part? So what's the problem? Expectation as well as reality. With this profile picture of professors, right? It's a dating pic. But we actually meet them, you look like, oh, they just came out of prison. So this is the reality of much of the data that we collect from ESR spectroscopy. So this is what we expect. And what we get is this, which sort of hurts because we have all this modern technology and how to get rid of it. So what it does, this noisy data, is it reduces resolution, as well as it masks weak signals, which provide important information. And what is the way to get rid of it? So the question becomes how to get rid of it. Just to let you know, this is not me. This guy has hair on his head. Um, so what has been traditional approaches that have been used to remove noise in ESR? One is signal averaging. So basically you repeat the experiment multiple times and then you average them and you get a better signal. But the problem with the signal averaging is it is pretty slow. To get an improvement of by a factor of 10, you have to repeat the experiment 100 times, and that's by the square root of n. So this is a very slow process, and the limitations as sample breakdown. Sample may say, well, I'm done. You're taking too much time. And then instrument may be unhappy, say, well, I'm not your workhorse all the time. And then there'll be sort of called teenage unstable samples. It say, I cannot stay there for so long. So these are many limitations which may affect us and affect our output. And then the second approach, which most of the people use, is higher sample concentration. So with the capabilities to measure at some micromolar and few micromolars, we actually collect data at tens of micromolar, sometimes at millimolar. So it works, it boosts the signal, but it comes at a cost. There are fear of aggregation, misfolding, and instability. But in many cases, it cannot even be prepared. So we are limited to only few samples that we can study. And more importantly, it may actually become physiologically irrelevant. You may get information, but how much that information is reflecting the real life, that is a big problem. So it's like something to this. If you put the sample in constrained environment, you all are working hard, no cheating. As you put them in the physiological environment, this is what we do. We are in the cheating mode. And many professors who are taking classes, know that all too well. So what are the other approaches? So one is the Fourier transform approach, which has been used for many decades, and which is the filtering approach, which many of you, if you use, that is the filtering approach which we call. So what does it do? It's like a prism experiment. If you have a white light, say like my face, and you pass through a prism, it decomposes the signal into different colors and say, well, I have multiple colors, and it tells you which color is dominant. So if you take my picture and pass it through prism, it will tell me which color is dominant. So we see I'm more reddish, or I'm more bluish, or less greenish. So it gives me that information. And that's what Fourier transform gives you. And similarly, you can reconstruct it by passing again through a prism and get the same image. In Fourier transform, same thing happens. You take this ESR spectra, take a Fourier transform, it gives you frequency information. So frequency information meaning how spectrum is changing with respect to each other, how each data points are changing. So you can see with this thing, it's a low frequency signal. A lot of frequencies are low. So that means the spectrum is changing very slowly in most cases. So this is akin to this, what you call passing your white light through a prism, where you get different color bands. Here you get different frequency bands. A lot of time, people who have been using data processing methods, what they do is they say, well, my noise, which is distributed across the frequency bands, and signal may be distributed at certain frequency band, I can simply take out that signal and leave the noise again. So I can get rid of my noise. But there's a problem. There's a fundamental problem. Noise is present at all the frequencies. So you can only remove this part of noise where there's no signal. But what about where in the frequency bands where there is both signal and noise present? You cannot remove it, because if you remove it, you also remove the signal information. That's a fundamental limitation of Fourier transform methods, that you cannot remove noise where signal frequencies already exist. And then there's a second practical aspect of it. How do you choose this cutoff? Should I choose it here, here, or here? Because we don't know about the signal. Sometimes we have some in priori information, but always all signals are different, and they have different frequency information. So if you choose it here, you will still have some noise. If you choose it here, you may actually distort signal. So you don't know where the actual cutoff point is. So some of the low pass filtering methods, which is also called smoothing, if you hear smoothing, that's basically low pass filtering. It does remove some noise, which you can see here, but it is also available some sort of signal distortion, as well as not removing all the noise. And the reason is they don't know what the cutoff is. There's a practical drawback, and the Physical drawback is they cannot remove the noise where signal already exists in the frequency domain. So, well, this is what we already have. And it's pretty disappointing, as you can see from Obama's face. I think he's both dejected and disappointed. And he's saying, is there another way? And his wife, Michelle, is all good. He said, of course, baby, there is always a way. And she's partying all the time. And she says, what do you do? She says, well, just have a method which can represent signal and frequency information at the same time. He says, what the hell? What do you mean? She says, Madhur will explain. So I will do that. Let's go back. Rather than going forward, let's go back to 1909 in the Germany. This guy called Alfred Haar. He developed a PhD thesis on orthogonal functional systems, where he said, here I have this picture. I get the frequency information, different color bands and frequency bands. What if I'm to see where those color bands are actually occurring in the picture? I want to see the location of those color bands and intensity of it. So if you just allow the red band to pass, you can now see my picture in the red band. Now you can see my red picture in the green band, and you can see my picture in the blue band. So you don't just get the how much band is present, but where in that picture location you have that information. So you can see the intensity distribution too. So that becomes a two parametric representation. One is signal domain, that is in this case it will be space, pixel location, and frequency representation, which is the color band. So you can see all these colors or frequencies with respect to where the signal location exists. And that gives you information, because now you can say, oh, my signal and noise may not have same frequency at the same time. So I have a much better chance of actually picking my signal and removing it. So this is the wavelet transform representation that he gave. He said, I want to use my frequency and signal displacement, basically signal location information simultaneously to probe my signal and see how it is distributed. So what he said was, divide the frequency into different subbands. This is the frequency band. And then you chop it into different frequency bands, and then see how signal looks in that frequency band. So currently we just knew what the frequency was. Now we can able to see how the signal looks within that frequency. And you can vary these frequency bands, as you can see here. So this is further, I think he developed it and nobody cared. And remember, this is 1909 when Einstein's, Haber, as well as Madame Curie are doing some fantastic science who care about wavelet transform back then. So, and there was no computers. So he developed this parametric representation, which was just mathematical curiosity. But in future, there are two problems. Well, there's a function which needs, which has to be applied to this input signal to get that frequency and time information, what that function should be. Haar said, make a rectangular function, basically chop it off into different lengths and then take a Fourier transform. The problem is, we all know chopping it off is not a good idea. It's like if you put a brake in your car, it takes a while to stop. So if you chop it off, you create a lot of discontinuities or distortions in the signal. It is good for certain applications, but not for all of them. Then this guy, J. Mollett, came in 1970s. And till 7 decades, nothing much happened about wavelets. What he said was, if you guys recall, in 1970s, there was an oil embargo. So there was a problem with oil extraction and there was a limited amount of oil. So oil company, he used to work for oil company. He said, I need to find oil, and I know my oil looks like a wavelet function. So I'm going to develop a wavelet, which if you get a seismic data, you can simply extract that data and pass this through this function, which is some a priori knowledge, and we will know where the oil is and by how much. So he developed this thing, and which became the first wavelet function to be used. Now, some of you also recall, you may not know about the oil crisis, but there's a speed limit in the United States that was introduced in 1970s just because at 65 miles per hour, it is much more efficient to drive. And the oil crisis went, but they never reduced or removed the speed limit. But there's a problem in this system. When you have a functional form, you're already biased your basically transform to a particular type of signal. And wavelets can be applied to anything. So that means if you apply to this face or these pictures, you don't want a functional form of these pictures. You don't want, oh, my face looks like an exponential or a cos x. If you have a longer chain, or divide by sine x2. So you don't want that thing. It would have been a convenient thing if we can represent a lot of things in functional form, but this is not how real life works. We need something which can extract features without having functional form, because there are a lot of functional forms which does not have, or a lot of features which do not have functional forms, but they still have patterns. So Daubisches in 1980s and 1990s came up with the idea of developing wavelets using fractals. So fractals are sort of wavelets, or they capture wavelet functions which can capture patterns without knowing what those patterns are, without having a functional form. But there has to be some pattern. So pattern means some sort of coherence. Something is having a structure. So if you see somebody's face, this is a structure, it's not a random thing, but you cannot define in mathematical form. So she used fractals to develop wavelet, which actually led to a wider application of wavelets. And so now you can probe any function or any image or any data without worrying about whether you're biasing towards a particular solution or not. But there was another problem. This is continuous wavelet transform. It's good mathematically, but there's a problem that how do you take it? There has to be a way to practically implement it. So these two guys, Mayer and Mallet, in 80s and 90s, developed a discretized wavelet transform, and then say, well, this is also too cumbersome. There's infinite number of combinations of A and B. So there's too much data to be processed. And they developed a particular form of wavelet transform, among other forms too. It's called dyadic, where you basically divide the frequency band by 2 and also use signal length by 2 to basically take wavelet transform. And then they did further thing, which is used to take wavelet transform, is using a filtering method. This is also a cumbersome process. You cannot use this formula to take wavelet transform. You have to use filtering approaches, which is actually given in my PhD thesis, chapter 1, and I'm happy to share about it. And if you see all the papers, they talk about this formula and this formula, but how to get from this formula to this formula to the final formula, nobody tells you. And that's what Fried picked up. He said, well, how do we do it? And we have to do all the mathematical calculations. And we found out this is how we actually take a wavelet transform. Now, why this formula? First of all, this is it's like a pulse sequence. There is no unique pulse sequence in NMR or EPR. So this is the most popular one. This is not the only one. What you have is, you have to preserve the input data and output data. Suppose you're processing this image. You don't want wavelet transform to have more data points than the input image. It takes a lot of storage space, which at that time was not present. Second thing is, this is a binary representation. You can see it too. And for computers, which is of binary nature, say 0 or 1, this is a very efficient representation. That's why they chose it. So somebody who remember those old TVs, so these were frequency based. They used to have antenna and used to get this continuous analog signal. But these modern televisions is all wavelet based. And you can see, we can, even in this video, we can enlarge and our images, because wavelet transform allows that thing. So this is a living example of application of wavelet transform in our day-to-day life. So anybody who's interested more and likes mathematics, these two books are there. Interested, do read it. It has a lot of complex mathematical gymnastics in here. So you're going to love it if you are a mathematics loving person. So what is discrete wavelet transform, I told, but what does it look like? How does an EPR spectra look in a wavelet domain? So this is a noise-free EPR spectra. This is the frequency information of this EPR spectra. What we do is, we divide the spectra into this band. We look at this frequency band, first a top half of it, and see how my signal looks at it, which is this part. So you divide this spectra into two parts. This is the red part, and project the signal in here. And then there's a remaining part, which is not yet represented. That's a low frequency that is represented here. So this is the residual data. This is the actual data, wavelet transform of it, but this is the residual data yet to be processed. So you divide into low frequency and high frequency and low frequency, and then project those signals. And for the next step, you take this remaining frequency band and divide into two parts. You take this part, divide into high frequency and then low frequency. And then you project this signal into this frequency band. So you can see, first of all, signal locations occurring where the signal is occurring, these wavelet locations, and you can see them through the prism of different frequency bands. And further, you can divide this part into two parts, high frequency and low frequency, and then project how my data looks like in that frequency band. So if you want to reconstruct the signal, you take this residual part and these wavelet components, and you can easily reconstruct it. And if you want to reconstruct it from this level, you can take this residual part and the remaining and the wavelet components and reconstruct it. So this gives you the signal localization. Now you can see occurrence of the signal in a particular frequency band. And you can also change your width of the vertical frequency bands to see a narrower or a broader if you have a particular type of signal. Other thing to notice is, and that is particularly important for denoising, is this is centered around 0. So if you understand the what called frequency systems, this is non-zero frequency. So it is only measuring the change. It is always centered around 0. And the advantage of this having this change is, if you even identify noise, the bigger problem is not the identifying, but what to replace that component with. So if it is centered around 0, you can put that thing to 0 for denoising. You don't need basically guess any value what to replace this noise value with. So concept behind denoising. So till now there was no wavelet denoising, not even thought of. And in mid 1990s, wavelet denoising concept came. So there are traditional approaches. Suppose in a noisy signal, we have both signal and noise. So consider this water as noise and things in the water as signal. If somebody tells you, well, I want a thing in the water to come out, you don't know what that thing is. You need to know whether it's a shark or it's a stone or it's a ball, because unless you don't know what to pick it with. If it's a shark and you put out your hand, you are going to lose your hand. You're not going to get the shark out of it. So this is what the most people did. They said, I want some a priori information. And then when I have a priori information, I use specific tools to extract this object. And in that case, you extracted the object, and what the remaining was just the noise. In the second case, the concept of wavelet denoising says, well, I don't care about my signal. I don't know what it looks like. It can be anything. What I do is I simply drain out the noise. If you take this tank and remove the water, whatever is left over would be my signal. So say, as long as I know about my noise, I can use that information to remove the noise, and whatever will be left over is the signal. So you don't have to know anything about your signal at all to remove noise. You just need to know more about your noise. So this paper by D.L. Denoising in 1995 is a classic paper, which is, I guess, cited more than 12,000 times. This is the which introduced wavelet denoising to rigor. He says, if you read this abstract, reconstructing an unknown function, basically without knowing what the function is, from a noisy data, which has independent and identically distributed Gaussian random variables. Basically, in other words, if your noise is random, we can reconstruct an unknown function. Now, he said Gaussian random variables. Later on, it proved that you can do for other random variables such as Poisson and anything else. So he showed mathematically we can easily recover it. And he himself said these two properties are unprecedented in several ways. So he realized this is a new concept back then, that you can just remove the noise and get the signal. So what does that mean? That paper is very long and lengthy, and anybody who's interested, please go and read it, but I can give you a gist of it. This is signal, this is noise. So you get a noisy signal. So this is how your noisy data say look in 1D, yellow. This is a noise-free data, green, and this is noise. If you take a wavelet transform, as I said, it is signal location and the frequency band. You have a 2D representation. So if you look at noise first, noise, although in one dimension, when it goes to 2 dimension, it's sort of reduces, because now it is spread out in 2D space. So first of all, its magnitudes gets reduced. Signal is not occurring at all frequencies and all locations and all. So it will be also occurring at just few places. Noise is occurring at all places with a reduced magnitude. Signal, on the other hand, because it is just limited in basically frequency and time, it is only occurring at small places with a higher magnitude. So you have now you have this potential, and if you add this thing in noisy data, you can see these green spots which will have some noise, but the remaining spots will just going to have a noise. So if you just remove this red spots, you can get a denoised data, which we actually get. This is the procedure. If we follow, we can actually get a denoised data. The question is how similar it will be to my noise-free data. So the mathematics worked down. They said this is the our noise will be very little. meaning that our signal will be too high, although I'm saying it's slightly lighter green, but it will constitute 99% here. Only 1% will be noise. So the error would also be very small. So you can see L is the length of the data, and log L, which is the again the length of log of the length of the data. You can see if you divide by them, it is very small. So in general, it is a very small data error that we get from it, and it's showed in that paper. So let's see how noise looks in wavelet domain for the EPR data. So I showed you that, well, this is the 2D representation, but what does that 2D representation look like? So this is one case where you can see if you have a frequency, you have noise in here, and this is a noise only case. There is no signal existing, just the noise. Second case is you have both signal and noise present. So in this case, you can see there's an overlapping signal and noise, and in frequency domain, there is no way to basically separate them two. But once you project that thing in location information, you can see this is all noise, this is all noise, and this is signal. So if you just preserve these coefficients, we are good to go. And in the third case, we have a very little noise, and where signal is mostly dominant. So you can see a very third case where there's very little noise and the signal is dominant. And they all three are from the same spectra. So they all collectively form the overall signal. So if we do an intelligent way of denoising it, we can remove this noise. So I did apply that thing. There are standard methods, and I've said, okay, theorem is good. Let's now apply the standard methods. But you can see, well, they didn't do a good job, and that was very disappointing. You can see some of these results here. There's still some noise left. In some cases where you can see noise is being more or less removed, but there's a signal distortion. It is the blue one is the reference signal. So you can see the black data is not overlapping with the blue data. So either it is not removing the noise or it is distorting the signal. And that's very, what do you call, a bad news. And actually I got angry. The first thing which I said was WTF, 2 years of my life gone. So what to do? So first to get rid of your anger. So I play cricket, and this is me hitting the University of Pennsylvania team out of the park. When I got this result, I had a cricket match and they didn't like it because you can see I hammered them out. Once your anger subsides, you say, well, what's going wrong? So I checked it. I said either fundamentals are wrong or the technology is wrong. Turns out principles and fundamentals were correct. It was the methods developed which were not efficient. Same as old MRI machine. Remember, this is a 1970s MRI machine. Nobody wants to get in there, right? But the MRI principle is all good. There's nothing wrong with MRI basically concepts. You need to just develop a better machine or better methods so that we can do a standard clinical imaging. So I realized wavelet denoising, the concepts are all good, but we need to develop a method to realize those goals. So what did I do? 4 things. First, if you look at the standard wavelets, there are 3 conditions where there is all noise, signal and negligible noise. What we do first, we need to identify these 3 components. They are not the same, and you have to tag them accordingly. If it is all noise, you have to say it's all noise. If signal plus noise, you have to say signal plus noise. And if it's noise with negligible noise, you have to say it, because if you're applying a noise thresholding algorithm, the 3 mechanisms for them would be very different. You don't want to club them together because then you get a distortion. You have to make a trade-off. Either you remove all noise and create signal distortion, or keep some noise, which is not good. And standard methods, and this is the first thing that we introduced in here, which was not existent previously, to how to calculate this thing. And we used the concept of sparsity. What we did was take the highest magnitude of it and divide by the magnitude of all these coefficients. So if it's too noisy, you can see in this case, the value will be too small. If it is less noisy, this value will be too high. And if there's some sort of noise present, there will be somewhere in between. So we developed this criteria and then choose a cutoff so that we can have separate these things out. Now, the second thing was how to get rid of, basically how to choose a noise threshold. So in this case, you simply remove everything once you know it's all noise. In this case, what you do is you have to choose a threshold, something like this on the positive axis, something like this in the negative axis. The previous thresholds, what the problem was, they didn't actually calculate the actual data. They didn't calculate noise thresholds from actual data. they took the length of it and took the log of it and use a median to basically calculate the noise threshold, which is not an efficient way of doing it because you need to incorporate the actual data set. So we here incorporated the actual data set to calculate the thresholds using mean standard deviation and a skewness factor. Now, second thing is you will see ideally, if you just look at the magnitude of the positive and negative should be same. But we realized that's not the case actually. You should have a separate threshold for positive values, separate threshold for negative values. They may be same in magnitude, but it's not always the case because we are dealing with discrete data. There's always some skewness in present. So sometimes it may happen, noise may be less than the signal magnitude in the positive, but it may actually be greater than the signal magnitude negative. And you don't want a situation where you have to remove this negative coefficient just because to remove this noise. So why not have a separate distinct thresholds for positive and negative? Third thing was a lot of people use soft thresholding. So soft thresholding has been used. We all know it's a good thing because it's signal plus noise. So you need to remove the noise. But when you are taking a wavelet transform, you're already doing the soft thresholding kind of thing because this is occurring at the same location. So all the noise present here also got filtered out here. So wavelet transform per se is doing some sort of soft thresholding. So what we need is a hard thresholding. If there's a threshold below it, it was put to 0. Anything above it, we keep as it is. Because if you apply soft thresholding here, we may actually end up distorting the signal. And the third thing that we did few more changes, but most important among them was, these are all detailed components, basically wavelet transform. There was a residual component which I showed, right? The approximation component, which was yet to be taken. That also has a noise, that's a low frequency noise. So we have to apply all three mechanisms to that component too. And then only we can remove all the noise. Otherwise our low frequency noise will still be present. So let's look at the result. So this is a temporal data, 1 millimolar concentration. This is our C13, C12 peak. And you can see we can recover that part. But the more interesting part is C13, which is primarily suppressed in noise. Now, if you apply the C13, you can see main peak was 15. So we can easily recover it. This is 0.5. Now, you may say, how can you do it for 0.5? The answer is, once you project this signal into 2D space, noise spreads out and signal still stays at location. So you get a signal is higher in wavelet domain and noise is less. So now we can easily recover. But this other interesting factor is this curly hairs. If you say like, this is your crush main peak, it has curly hairs, you need to recover that too. So we are able to recover that part too, precisely because that part is boosted in wavelet domain and noise is spread out. One thing, if you work on temporal data, you will see one thing we have not recovered. That is N13 peaks. And that once I was told, I said, what are N13 peaks? And then it turns out what happens is when we say we are recovering signal to noise ratio of 0.5 or 15, we mean is that particular peak height. We don't mean overall signal. It's not that you can have any height here and any small signal here, we're going to recover it. Any peak which is having 0.5 or greater, we can recover it. Anything less than that, we cannot. So there can be N15, which is say 0.1 or 0.01. We cannot recover it because we cannot identify that in wavelet domain. So only thing that we can, only component which will have a higher signal magnitude and lower noise magnitude in wavelet domain can be recovered. Second, I think some of the best experiments that you do is not what you do, what somebody else does. So this data is collected by Boris Zikovsky in our lab. So this is the noisy data. And after you denoise, you get this. These are hyperfine spectra. And but the problem is you cannot get a reference spectra for it. So you have to increase the modulation just to get a reference data. So you can see it matches perfectly. And if you look at the noisy and denoise data, and this overlaps. So now it may sound like a bad thing because it's like a snake oil, like what are you selling? Remember, signal here, although is suppressed by noise, but once you represent in wavelet domain, it is only occurring at few locations and it is having features, so it is represented by higher magnitudes. Noise, on the other hand, is spread out. So what happens in wavelet domain, you get an easier picture. In fact, these are the easiest data to denoise. previous data was much more difficult because signal is spread out. In this case, it's such a fine pattern that you can see very only few coefficients existing in wavelet domain. You just need to recover that. So if you have a spectra, we have a software, you just split it in and you can see that signal in wavelet domain itself. Now I want to get into a case study because once we collect the data and denoise, that's easy. But the problem is, if you are trying to start a study,
just a short comment, Matur, that it's 38 past. You can still use some time. It's just that you're aware.
Okay, thanks. So now the question becomes, if you want to study, you want to say, is there signal exist or not? If signal exists, the problem is, then you want to spend your time and effort to do that study. If there's no signal, you don't spend time and effort. So first, there's a data or not. So this is with Brian Crane, collaborator, and the problem with having collaborators is actually they believe what you do. So this is the data that they gave it to me. This is 0.1 SNR, which is a very bad data. Even I was surprised that it got denoised, and I will tell you why we got successful. So if you collect for 1 microsecond, you get this high SNR. If you collect for 2 microsecond, you get this poor SNR. But if you reconstruct this distance, it's a broad one. And this sample is in detergent, so it has to be a narrow peak because detergent doesn't allow much flexibility. And if you collect noise, you get this noisy data. With denoising, you got this peak. And that led the study to function. Then people worked on that study and get that output. So this paper got published. But if you see this paper, this data does not exist. They did a proper experiment and got it done. So this can be simply used just to say whether your signal or data exists or not. Then I think coronavirus, I don't think we need an introduction for it. We all know what it's doing for us. Luckily, sometimes luck has it in your favor. So Fried and collaborators in 2018 started working on coronavirus, and what luck it was. I think never a better application for that. So now we have a situation and ACERT is open studying coronavirus. So what they devised a technique called fast MR, fast scanning, where they collect data for 5 minutes, denoise, and then spectral stimulation, because you don't have much time to do all the, go for longer collection time. So this is another application of wavelet denoising. And if you want interested in seeing how the COVID-19 looks in CW spectra, this is your exclusive data. More will be coming, both of pulse dipole or CWSR from Fried's group. And but this is, you can see, it's pretty party loving data. It's a lot of motion and moves. These are the publications. We also have a software we can log in and basically play with it. And these are the publications. Those who are interested can actually read them. There are much more details in it. At the end, I want to say that it's a 3-body problem. We have physical chemistry, we have biological structures, we need data processing to solve the problem. Same as the way Uber solved the transportation problem with cars and people. So where we are headed next? Basically tens of micromolar that we use to do an experiment, we want to extend it to sub-micromolar. That should be a standard basically mode of experimentation. And for that, that's what I'm trying to develop, data processing methods. So like the way they have been together for 70 years, we want this data processing spectroscopy to be in bed and have a dipolar coupling for so long or even longer. Acknowledgements, I want to thank 3 people. Fried, I think I wanted to be a lawyer, chose academia because my experience with Fried. We did have bonding and both chemistry. Crane, who basically initiated to get me hired in the department, and Maroon, who basically, he's actually best critic of wavelet denoising, but also helps me basically getting started and helping with grant applications and finding new funding opportunities in NSF and DARPA. This is my basically still hangover of PhD. What I learned is PhD is not a degree to earn, but an experience to live. And is wavelet denoising a snake oil? I don't know. I'm just hanging around. You decide. This is me. I think Nino already said it about my background, but I wanted to tell that this is my life motto. I will always be there whenever I need you. So thank you.
Thank you, Matur, for the talk. Now you can ask your questions. I just have to make sure that I see you. If you raise your hand, somehow I cannot.
I think Jason is raising hand.
Yeah, I just have a problem seeing the participants panel. Sorry. Okay, Nick, I think you can unmute. Yeah.
Yeah, great. Hi, Mada. Thanks for the really nice talk. I really enjoyed it. Thank you very much. So when you do the wavelet, the discrete wavelet transform, you have a choice to select, well, you must select the essentially the number of frequency bands or something similar, right? How many slices you take. So how do you make that choice when you don't know if your signal is, say, very, very high frequency in the second case you gave, or very low or lower frequency than the noise in the first cases you gave? Could you give us some insight?
So that's actually a good question, because at present we are using a standard infrastructure. We haven't developed any of our own. And with standard infrastructure, there is a formula. If you have such a data length of 512, it takes the log of the data length, log 2, and that is the maximum frequency bands you can have. So that would be 9. And what it does is, so if you have a frequency band, say 1 to 1000, so 500 to 1000 will be band number 1. 250 to 500 would be band number 2, and basically 10 remaining band divide by half. So now the question is, yes, this is working, because if you go to a lower frequencies, you have better resolution, frequency resolution. But in some cases, if you have a really high frequency, you may have to change that part. You may actually need a smaller bands at a higher frequency. But the data which I showed you, which have a high, echo, remember that when we add noise, it also increases the frequency band, because there's now higher frequency. So the first band primarily turns out to be noise. From the second band is where you start seeing signal coming in. So, but I think that's a really good question. And that's where one of the limitations is. When you say SNR of 1, so if you want to go below, that is one thing we are going to change, frequency bands, because we need resolution on those frequency bands.
Okay, then Jason.
Yeah, great talk. It's every time I see you talk, there's always something new to learn about this wavelet analysis and the denoising. So thank you. My question more is along the lines of the limitations, and it's very clear that the assumption that you're making is that it's additive noise. And so when you start talking about things like phase noise or things that something along those lines, you have to worry that the concept of noise is no longer additive, and that it's actually changing in a different way. And I think if you can make some comments on that, that would be great.
That's actually, again, a very good question, because here we are just dealing with additive random noise. Because if you are extracting noise, as I showed, if you are just drawing out the water, we should know what water basically. So here, anything other than that, any sort of systemic noise, at this point of time, we cannot do. But there is a way to get rid of it. If you know that there's a systemic noise that exists, say an artifact or some sort of at a specific location where signal does not exist, you can remove it.
Yeah, of course, but I'm more interested in the noise where, I mean, so this isn't a I'm helping you in saying that it's not snake oil, because when you understand your noise, then absolutely you can remove it in the additive form. I just worry that when you have things like phase noise and you have waves that are on the order of your sample or of your signal, that is a limitation for this. And it's nice to fully understand where your parameter space is for this algorithm.
Well, I think that's a good point. I think just random noise. And in fact, what we have found is sometimes it's good to have noise, because if you remove random noise, it exposes your artifacts, which sometimes can be pleasant and unpleasant. So we can't get rid of artifacts of phase noise. I think, yeah, that's a good point.
So we can make better instruments if we get rid of the random noise, and then we can work on our instruments to get rid of the systematic noise.
Yes. I think that's a good point. That's a good.
Yeah, then I have a question from Ilya from the chat. So I think his mic is not working. So he asked, the assumption appears to be that useful signal is localized in the wavelet domain. Is that always the case for EPR or DIR data?
That's a good question, because I think for that, I need to have a wide range of knowledge of EPR data. Whatever I've encountered, answer would be yes, but there's a data where your signal exists. Basically, if it's a stationary data where all the frequencies occur at all locations, yeah, then it will be a much more challenging case. But in most cases, signal is not stationary. That is, all frequencies are not occurring at all signal locations. That means it can be localized in wavelet domain. I hope that answers your question. But we can always talk offline, Ilya, if your mic is not working.
Okay,
So,
then Tufa.
Hi, I don't know if you can see me. My question is about the data which is the most applicable for wavelet transformation or Fourier transformation, because what you were saying at the start, you described it pretty nicely that the disadvantage of Fourier transformation is that you have to choose a frequency cutoff, right? But for wavelet transformation, you have to choose a noise cutoff, right? And so you showed some data where I don't know what exactly it was, but the frequency was really high and then the noise was sort of matching it. And you said that this was the best data to analyze. So can you speak a bit more about that? What is the best sort of data set for wavelet transformation?
So what happens is when you see high frequency is actually, we use relative terms. It's higher than the low frequency. So noise is always higher. But the thing is, anything which has patterns, say sinusoidal function, which is a sort of pattern or sort of oscillations, they get concentrated with very few coefficients, both in frequency domain and wavelet domain. Now that means if you have all the signal put in with all energy at localized just a few coefficients, their magnitude will be much more higher.
Okay.
Domain. So noise is spread out. So now it's easier to basically capture because their signal magnitude is much more higher in wavelet domain. If they had, say, non-periodicity, then that will be represented by more magnitude and spread across.
Okay.
And create a smaller barrier between noise and signal.
Okay. Thank you. I think about that.
So one thing I would say is if you have such data, in fact, these are data which is you can easily see in wavelet domain. What you can do is just upload your data to the software and just within wavelet domain, you will start seeing those hyperfine lines.
Okay, thanks. Then we have another question by Dennis.
Hi, this is more a basic question. So what are the prerequisites to analyze data at all with wavelet denoising?
Can you repeat it? Your voice was not clear.
Sorry, that's my connection here. So what is the prerequisites? So what conditions have to be met by the data that wavelet denoising can function?
We have already said that SNR of about 1. The peak which you are looking at should have SNR of 1. So if you have, say, anything less than that, it is not going to work precisely because noise is going to dominate in wavelet domain. And it will basically much more dominant. Now, so that is one thing. Second thing is noise has to be random. If it is anything more than that, then you cannot remove that noise. I hope this answers your question.
Yes, perfect.
So yeah, and I think I must point in this follow-up thing that if you have, say, multiple peaks, some of them is greater than 1, some of them is less than 1, then you only recover which is greater than 1. So if you are having a spectra which has less than 1 and greater, then you only recover those part of it, not all of it.
Okay. Any other questions? I don't see any. If that is the case, then thank you again, Mathur, and thank you for all the questions and the answers. Then from my side, so next week we have Fabian Hecker from Marina Donati's group. It's talking about 17.0 hyperfine spectroscopy, if that is interesting you. And again, if you know somebody or yourself would like to give a talk, please tell us. And otherwise, I will wish you a nice weekend or rest of Friday, depending on where you are. Okay, bye. Or maybe Mathur stays. So if somebody wants to talk more, feel free. I probably have to go in a few minutes, but you're co-host now, so it should work. Okay. But I stopped the recording.
Thanks, Nino. Thanks, Nino, for pointing me down because time about it. I just lost track of it. I usually have a clock with me. And basically,